let's quickly go over this triple oscillator. This is just a simple extension of the previous problem of the double oscillator. So we have the same symmetry group in here. So basically we have just a reflection symmetry, but this time the mass of the middle object is different than these two objects. So that's still consistent with the symmetry. These two springs are identical. These two springs are also identical. Okay, so let's just quickly do this. Again, the symmetry group is the C2. It contains identity and this reflection, so I just call this again sigma. We have a vector space formed from the coordinates of basically displacements of all of these three objects. So I'm going to call them as x1, x2, x3. So we have a space, a vector space of 3 dimensions. So as a result, we have a 3-dimensional representation. So this is in R3. So we have a representation A of, basically A is a representation from the group to the, 3 by 3 matrices. A of identity is the identity matrix, so that's the simplest. So I need to find A of sigma. So I know that A of sigma changes the x coordinate to x prime, where let's see, this mass is moved in here to that location, so therefore its displacement becomes minus x1 along that way. So in any case, you can just think of it like that. So in the new reflected system, so the third mass has a displacement of minus x1, and similarly the first mass has a displacement of minus x3. And then finally, the middle mass has a displacement of minus x2. So that's A of sigma applied on x. So therefore, A of sigma is, I'll just write it in this corner. So that's equal to 0, 0, minus 1, minus 1, minus 1, 0, 0, 0, 0. As I said before, only the diagonal entries are important right now because I need to compute the trace. So you can see that the trace of A for sigma is equal to minus 1. Let's write down the group characters. These are the conjugacy classes. U1 and U2 are the two representations. U1 is the trivial representation. U2 is this other representation. A is a representation whose character for identity is 3 because it's a 3-dimensional representation. For character for sigma is minus 1. So from here you can see that A is actually a direct sum of U1 plus 2U2. So therefore I can make some kind of a similarity transformation in here, which is S transpose S minus, I don't know if this is an orthogonal matrix or not yet, so let's just say it like this, where the first block is U1, the second block is U2, third block is U2. I didn't write these well, so let me rewrite them again. So the first block is U1, the second block is U2, third block is U2. These are of course 1 by 1 blocks, but in any case, so there is a representation where, so there is a similarity transformation where this is basically diagonal, and we would like to find these. So that's it. So what are the normal modes in that case? So first I need to identify this U1 mode, because this is the unique one. So this is the mode where there is a vector in there. Let me call this as A1, where A of G applied on A1 is the same thing as U1 of G applied on A1. But U1 is the trivial representation, so therefore this is a vector that remains invariant under the action of the symmetry transformation. So in principle, in particular, of course, it is A sigma. So from here, you can easily see that this A1 should be equal to 1, 0, minus 1, because you know that the reflection basically changes these two and changes the sign of everything. So only this vector remains invariant under that. So we just need to do an orthogonalization. All right. So next, what are the, there are actually now two different subspaces in which the vectors transform like a U2 representation. So therefore, there are these two vectors. Doesn't matter which one. So each one is actually transform like U2 representation. And the same thing for A2 prime. I'm writing both of them because I'm somehow spending too much time on this. And I would like to find them, but of course I'm not going to spend too much time in there. What I need to do is basically say that both of these have to be perpendicular to A1 because this is a unitary representation. So therefore, I can choose A2 to be a vector which is perpendicular to that mode. What can that be? For example, this might be 1 over root 2, 1, 0, 1. And the other one might be 0, 1, 0. Right? So I'm choosing them to be normalized. I also make sure that these two are orthogonal to each other. So somehow the orthogonality of these two and these two are guaranteed, but I'm just going to do it like that. All right. So I don't know if this is a displacement pattern for a normal mode, because I don't know if these two are coupled or not. I don't know that, but somehow group theory tells me that at least this mode is uncoupled from that mode. That's the only guarantee I have. But for the coupling of this mode with that mode, I cannot do anything. So I need to somehow solve the problem at that point, right? So basically at this point, the identification of the modes is finished. But I'm going to do it like this. So I'm just going to write X. I'll just show how the normal mode pattern, normal mode coordinates can be obtained. So I can write this thing down as psi1 times this vector A1 plus psi2 times the vector A2 and plus psi3 times the vector, let me call this as psi2 prime. Doesn't matter much. So I'm going to do this, but you can easily check that. This can be written as, just remember how you do this matrix multiplication. I can do this as this kind of a matrix multiplication. So I first prepare a square matrix in here, where on the columns I write all of these vectors that I have just found, the vectors that I have identified now. And this is just a column vector where the components are just normal mode. The coordinates that I have introduced. So I know that psi1 is a normal mode coordinate, but I still don't know whether these are normal mode coordinates or not, right? So there's this kind of a complication in here. So this is my S matrix. So that's the basis change matrix. So this matrix is given by this 0, root 2, 0. You can easily check that this is an orthogonal matrix. I could have written this in some other ways as well. So this A2 prime. So I could have changed these two places and things like that, but at this point that's not important. So let's continue with the problem. I think I'm going to solve the problem in here and write down the matrices, but at this point, identifying, I don't know, some, coordinates or simplifying the problem is actually enough. But let's just go ahead. This is M1, sorry about that. Spring constants are K2, K2, K1, K1. So I'm going to assume that this is already in its equilibrium length. So as a result, if this moves with x1 displacement, x2 displacement, and x3 displacement, in that case, the potential energy is 1/2 of K1 times x1 squared plus 1/2 of K2 times x2 minus x1 squared plus 1/2 of K2 times x3 minus x2 squared, and then 1/2 of K1 times x3 squared. So you can see that this is 1/2. So let me just use a common 1/2 in here to make things simpler. So I'm going to get K1 plus K2 x1 squared plus K2 2K2 x2 squared plus K1 plus K2 x3 squared. And then I have from here the middle term, which is minus 2K2 x1 x2, and here minus 2K2 x2 x3. Right, that's my whole expression. So if I write this thing down as like x transpose kx, where k is the spring constant matrix. All right, let me just squeeze it in here. So that matrix is a 3 by 3 matrix, but this entry is K1 plus K2. The middle entry is 2K2. The last entry is K1 plus K2. 1 is coupled into 2 with a coefficient minus K2. 2 is coupled into 3 with a coefficient of minus K2 too. And these entries are equal to 0. What do I want to do? So there's one more thing. Yeah, we need to do the Lagrangian, but let's just write it down like that. So the Lagrangian is 1/2 of x dot transpose mass x dot minus 1/2 of x transpose kx. What is the mass matrix? Mass matrix is this M1, M2, M1. It's not that simple anymore. What's K matrix? I have just written this thing down. So that's K1 plus K2, 2K2, K1 plus K2, minus K2, minus K2. All right. So what I want in here is I would like to change the coordinates now. So I just write x as s times psi. So in that case, the same Lagrangian can be written like that. This is psi dot transpose. Let me write it down like that. So that's m tilde psi dot minus 1/2 of psi transpose k tilde psi. So what is m tilde? M tilde is this S transpose MS, and K tilde, well, it is K transpose, sorry about this, I was thinking about something else, S transpose KS. So I'm thinking about finishing the problem in here because I don't want to do these calculations in there. But you're going to find that this M matrix is of this form. There's 1 by 1 entry in here and a 2 by 2 entry in here. And K tilde matrix is also in that form. So this basically tells you that the this U1 mode that corresponds to the first coordinate psi1 is somehow separated from the U2 mode. So these entries are equal to 0. This tells us that the that U1 mode is uncoupled from the other ones. but the other two are coupled to each other. So as a result, there's still a 2 by 2 matrix in here. And so as a result, you have to solve the equations of motion still. But this time the problem is simpler in a way. So instead of solving a 3 by 3 matrix problem, now you need to solve a 2 by 2 matrix problem. So I'm sure that that problem is also simpler, but I don't want to carry out this matrix multiplications in here. So if you are curious about finding the frequencies in there, please just go ahead. But so I'm just going to stop in here.